basic part of this, I think most people know this, is that we get the physical world, we have to get the physical world into the digital world, and we do that with transducers or sensors, and I'm going to use them interchangeably for the course of the lecture, and you can pretty much do so as well. There are some people that will argue with you about the specifics of what each mean, but that's okay. We've got a wide selection up here. Most of these are available from SparkFun. If you haven't gone onto the websites like SparkFun and Adafruit, below some of these websites that sell these little sensor breakouts, it's worth looking around to see what's available, and it might help you decide exactly how you're going to implement your project that you're doing. So up here we've got a weather station. It's got wind direction, wind speed, and rain amount. So these sensors would put out something like a resistivity change based on the wind speed, and the wind direction and the speed and rain actually just put out pulses. They just close the switch. So you count how many pulses per second, and that gives you an idea of how fast the wind is, or how many pulses the rain gauge puts out tells you how much it's rained. Down here we've got a temperature and humidity sensor. This actually outputs a digital signal. It doesn't output an analog voltage. You talk to it using a digital protocol. And this one is relatively expensive. I think it's about $20, which is expensive for this kind of stuff. Not expensive in the grand scheme of things, though. This is a geophone that we use for ground motion, so ground velocity or ground acceleration, depending on how you have it set up. And we can use that to measure, for example, if you put one out around here, you'll see quarry blasts that they do just outside of town every day or so where they're quarrying rock. This is a soil moisture sensor that SparkFun has, and they've got a whole note telling you how to use that. A Geiger counter. So I don't know if anybody's messed with these much, but this is a tube that when an ionizing radiation particle goes through it, it conducts electricity for a very short amount of time, and you can count those and get an idea of what the radiation level is of ionizing radiation in an area. And then the top right is an ultrasonic distance sensor. So that actually transmits an ultrasonic pulse, a very short chirp of sound, above what we can hear. I think it's somewhere in the neighborhood of 40 kilohertz. And it goes till it hits something, it bounces off, and this times that time of flight and tells you how far away it is. It's only accurate to about a centimeter, plus or minus, but for a lot of applications, that's good enough. And this is one place where you have to know everything that can affect your transducer, because if you point this at something that is stationary, say I were to set it up on a tripod and point it towards the wall and record it for a few days, you would see it looks like the wall moves back and forth in a very systematic fashion, which we know it doesn't. It's because the speed of sound varies with temperature. In fact, it's 0.6 meters per second per degree Celsius, and so it's going to affect your readings if you don't correct for it. And almost every transducer has some kind of temperature dependence, and it's generally pretty awful to try to do corrections in the house. But there are transducers that talk on a digital format, and there's a lot of different protocols, but the idea is you have your microcontroller or your computer or whatever the master device is. So in this case, here's the master device that's an Arduino. And you've got a bunch of sensors that are all on the same bus. So remember, a bus is just a set of interconnected things that share a conductor. So we've got SDA, which is data, SCL, which is clock. We'll go over that more in a second. And we've got, in this case, 4 sensors on this 2-wire interface. There's a lot of these different interfaces out there. There's one that's called I2C, SPI, SPI, CAN. This is the one that's used in cars. It stands for Controller Area Network. Everything on your car is connected to the CAN bus. That's how somebody can break out your taillight, connect to the CAN bus, and start your car through the taillight socket. So there are advantages and disadvantages to having everything on one bus. And we'll talk some more about them as well, I think, in maybe the next lecture. But the process of data acquisition has these 5 basic steps. So first you have the physical system, which is what we actually care about generally, and what we want to sense. You get your transducer or sensor to actually turn physical system into some kind of electrical signal, but generally that signal isn't good enough on its own. Especially in geoscience, we're measuring very small signals, so you have to have some kind of signal conditioning, where you generally do things like amplify the signal, or buffer the signal, or maybe even filter the signal to get some noise out of the signal that you don't care about. And then it has to go through, generally, an analog to digital converter, assuming it's an analog transducer, which this takes some analog voltage, any voltage, let's say between 0 and 5 volts, and turns it into a digital number that your Arduino or your computer can store and can understand. And then the value from the ADC gets passed to the computer, where you do whatever you're going to do with it, real-time analysis, control, storage, whatever. So we're going to go through this process for a simple physical system. Let's say we want to measure air temperature. So the physical phenomena, if you really think about what air temperature is, it has to do with the speed of all these little molecules bouncing around in your air parcel or in this room or whatever. And this is ideally an animated GIF, but apparently there's no keynote. So that's the physics of what we want to measure. Our particular problem is, let's say that we're on Hoth, and we want to know what the air temperature is. I think Peter's the only person who's seen Star Wars. But, so let's say we're on Hoth. We want to measure the air temperature. It's pretty cold, but we want to know how cold, and we want to maybe know if Luke can survive. So we need a transducer to do that. And there are a lot of different temperature transducers. We're going to have probably 2 lectures, I think, that we're on about different transducers for different things. Right now, I'm going to say, well, let's use a thermistor. So this is something that it changes its resistance based on the temperature in an unfortunately very high order polynomial way. But not everything is linear. So this is a little piece of silicon down here. And if you were to connect a multimeter, set to measure resistance there, and breathe on it, you'll see the change. These are pretty cheap. We use them a lot. Probably buy one like this for under $5. But if you notice on your Arduino, there is no resistance port. There's nothing that you can connect to measure the resistance of something. So we have to condition the signal into something we can measure. On the Arduino, we can either talk digital signals, which this is not, or we can measure an analog signal using these A0 through A5 ports here on the side, where they take voltage and they're an analog to digital converter on it. So we're going to use something, in this case, called a voltage divider, which we'll go over at the end, because it's what you actually build on your breadboard. So this would be the symbol for our thermistor, and then we've got some fixed resistor down here. This is connected to ground. That's connected to some positive voltage. Here they have 12 volts. In your case, it would be 5 volts. And then you measure a voltage out here. So as this resistance changes, the voltage out here changes. Like we'll look at the formula at the end. But you can think of it as sort of a ratiometric. Right? It is ratiometric, in fact. So now that we've got our transducer measuring the physical world, and we have a voltage out, time to go to the next bit, which is analog to digital conversion. Again, we're going to talk about analog to digital converters work another time. This lecture kind of hits a lot of things that we're going to cover in more detail later, because there are people that spend a very, very long time trying to figure out how to do analog to digital conversion quick and in the highest resolution way possible. But for now, we're going to say there's a box, in this case a green box on a black box, called an ADC. So if you have a signal, let's say we're looking at a sine wave up here, this could be like the power that's coming out of the wall, let's say, and it's plus or minus 120 volts in this case. It is a continuous thing in time and in voltage, right? So we can't get from 0 to 120 volts without going through every voltage value. And when you go to the ADC though, we have to sample at a discrete time base, right? So we can't measure infinitely fine precision of time. So you'll notice that this is a little chunky. That's not the projector. That's actually the signal. That we're only measuring at discrete points in time. So it gets a little bit modified by our sampling. And it also gets modified by how accurate our ADC is. Everybody good there? Okay. So this is a quick demonstration of how the resolution of your ADC can change what you get out of your signal. So let's say we take a sine wave, in this case it's between 0 and not quite 9 volts. And we sample it with 2 different analog to digital converters. One of them has a 3-bit resolution. So that would mean that it's got 3 binary spots, so 111 would be the highest value, and 000 would be the lowest value you can measure. So how many different steps are there in something that's got 3 bits in binary? How many different discrete voltage bits can this have? 2 to the n, where n is the number of bits. So it's 2 to the 3. Right, so it'd be 8, yes. So 8 bins. So you can see if we're trying to measure something that goes 0 to roughly 9 volts and 8 bins, it looks pretty cruddy. That might not be a high enough resolution for what you need to do. I mean, if you're thinking about, I'm going to load some sample to 10 megapascals normal stress, is it good enough that each step on your analog to digital converter is over a megapascal? Probably not. But if you go to something that has 16 bits of resolution, then it actually looks almost exactly like the original sine wave because we've got so many more bits. Somebody know what 2 to the 16 is? Y'all do it to Peters. It's Gary's doing.
65,000.
Yeah. So 65,536. That's a lot of bins to get between 0 and 9 volts. That's a pretty good representation. It's common in laboratory equipment to have 24-bit analog to digital converters. So there you're looking at many millions of bits. There are some companies that are now coming out with 32-bit analog to digital converters, so they're pretty experimental still. So let's calculate what the resolution of the analog to digital converter is on your Arduino. So does anybody know how many bits the resolution is on your Arduino? Probably don't unless you've been reading this stuff. It's 10 bits, yeah. So that's 1,024 to the 10. But remember, we're dealing with computer scientists and engineers and hardware people. So like any sane person, we start counting at 0. So it goes from 0 to 1,023. That's the output. If you were to connect one of these analog inputs to ground, you should get all zeros out. If you were to connect it to plus 5 volts, since that's its maximum range, you should get 1,023 out. There's going to be some noise in there, of course, but that's the idea. So to calculate this, you take the resolution of the ADC, which is the maximum number that it's going to output, 1,023 in this case, and you divide it by the system voltage, which is 5 volts in this case, is the highest we can go to, and that equals the ratio of the analog to digital converter reading that you get over the voltage that you're trying to measure, right? So the other way to think of it is you take 5 volts and you divide it by 1,023, and that gives you the number of volts per bin. So if somebody do that, that's great. We can figure out what the resolution of your ADC is.
204.6. Or you want color?
Yeah, so we want volts per bit.
0.04875.
That's good enough. So 0.0048, and we're going to call that 0.005 for now. So 5. Yeah. That's pretty small. That's pretty good for such a cheap platform, and that's going to serve you pretty well in what we're going to do today. And then once you've digitized that data, so let's say that you're just using this as the digitizer. Maybe you're not storing the data off to something from this, but you can. We generally connect it to a computer, or here you can see there's a logger that's directly connected to some kind of signal board. Here we've got a computer. This is a small version of the Arduino that you've got connected to my laptop, logging data. So you have to have some kind of data logging program. This can be that you're just sending text back and you're logging text to a plain text file. That's great for low throughput applications. You know, if you're collecting something at maybe a few hertz at the most for not a very long period of time. Otherwise, you end up with these mini gigabyte text files that can be difficult to use unless you've got the right software. You can also send back binary data. That's much harder to use because it's in the raw binary format. You have to know the format. That's generally what we do in a lot of lab applications. And there are a lot of standardized ways that you can store binary data, like HDF5. There's a format called TDMS from National Instruments. They're very compact ways to store large amounts of data. But for everything we're doing in here, we'll probably just use text files because everybody can load those on their computers. And then we have to do a calibration. So now we've got We had a number of bits that came out of this, and then we converted it to a voltage. So let's look at a bathroom scale. This is fitness scale that throws stuff up on the internet for you. And let's say that when you step on it, it says 2.45 volts change. So there's a load cell in there. It's just strain gauges, and it's measuring how much you're bending a little piece of aluminum inside. So that 2.45 volts, we need to know some kind of calibration factor that we've done either ourselves, or in this case, the factory did. And let's say it's one of these numbers, either volts per pound or pounds per volt, whichever is easier for you to internalize. And then you multiply the calibration factor, the appropriate one, by the number of volts. In this case, 67.4 pounds per volt, that's 2.45 volts. Gives you 165.2 pounds, and that's what you know display. Because in the end, the person stepping on the scale did not care how many volts they really care how many pounds they weigh. So you have to do this whole conversion from a change in resistance to a change in voltage to digital representation to a voltage representation to the final engineering units. You have to go kind of full circle. And there are a lot of things that can go wrong anywhere in that pipeline. All right, so if we go back to Hoth, we're trying to measure the temperature. Now we have a voltage coming out of our little resistor divider, and we can calculate what the resistance, because we know the equations for how resistor dividers work, of our temperature sensor. Unfortunately, like I said, the temperature sensor is wildly nonlinear, and you need something called the Steinhart-Hart equation. This is how you calculate temperature from the resistance of the thermistor, unfortunately. It's not that hard, but if you try to do everything on board in Arduino, remember, this is an 8-bit processor that kind of has fake floating point math. It thinks of everything's in integers, really. So try taking a natural logarithm with no integers in an 8-bit processor. It can get pretty tricky. Though we've got ways to do it. For example, some of these processors have log tables stored in permanent memory, so you can look at the log table and have a successive approximation. But regardless, you can implement this equation either on your computer after you record the data or there. And we would get out the temperature on Hoth. Probably be very cool. So there are two different types of analog to digital converter systems. These are the GeoPebbles that Sridhar and folks in the ICE group have been working on. So these are 3-component seismometers that they lay out, and they form like a mesh network and send the data back. And they're actually a really good example of one device that has both types of systems in it. In fact, so it's the same hardware, it's just how you have it set up. So the two types are a continuous system and a triggered system. So we generally use continuous data logging systems when we need to record a long period of time and we don't know when the interesting stuff is going to be happening in our signal, right? So let's say that we're monitoring the weather. This was called a meteogram. So temperature, dew point, these are wind speed and wind direction measurements. And we need to monitor the weather all the time because we don't know when the storm's going to be coming through. We want to keep this information for records. So this continually measures all these parameters once every minute and has done so for many decades now in the case of this particular station in Norman. So what in the lab would be continuous? What kind of continuous data logging applications can you all think of?
Confining stress.
What?
Confining stress.
Yeah, so you probably want to do continuous measurement of confining stress in some kind of experiment.
Displacement.
Displacement, yeah. I mean, we're not measuring them for years, but we're measuring them for the duration of an experiment continually, right? Anything else? Okay, yeah. All the stresses and displacements vary. Maybe we don't really measure temperature continuously, but we could. But there's the other mode, which is triggering. And this is used in a lot of lab experiments as well, and in a lot of field work. And so this is a commercial weather radar system. You see the golf balls that, this is what it looks like if you climb up the side. There's this huge parabolic dish inside that rotates around. And there's a transmitter, so this thing sends out a very high power radio pulse. And then it listens for the echoes of storms and clouds and anything that's floating around in the atmosphere. Smoke, bugs, bats, birds, all of it reflects radar energy. Now, what the system does is it needs to record very, very, very fast because these are gigahertz radio bursts that it's sending out. So you need to record gigahertz plus, right? or they do some radio tricks so they don't quite have to. But the idea is they don't need to continually record how much radar energy is coming back. They need to send out the ping and listen for some fixed amount of time and stop. Right? So this is like what you do in active source seismic, where you hit the hammer, it triggers the system, it records for so many milliseconds, and then it stops. Because you only care about the interesting part when you actually hit the ground and put seismic energy into the ground. You don't care about the continual recording for an active survey like you would passive seismology. So this is really generally used for very high frequency recording rates. So like in the lab when we do acoustic emission, we don't record, well, we do sometimes, but we shouldn't be, recording at 50 megahertz for 3 hours. That's an incredible amount of data. And in fact, there are very few data acquisition systems that can do that because you have a problem of how do you get that much data written to any kind of storage media. Even solid state hard drives would struggle to keep up. So then you have some kind of buffer, and the buffer fills and then you have to stop. So it's still effectively triggered. So for really high rate things, so we use trigger acquisition. And the other thing is you have to make sure that you're sampling fast enough. Is everybody familiar with aliasing? Or slightly? Alright. The idea is, let's say this red signal is our original signal. That's what nature is giving us or what our system is outputting. But we are only sampling, let's say these are seconds, we're only sampling it once a second. And so we would reconstruct this blue waveform, sampling it once a second, which is not at all what the actual system is doing. So we've completely fooled ourselves. And we're going to talk about this really nice, roughly 10-second period wave that we see in our data, when in fact it's not that at all. So there's a criterion for how fast that you should sample at the minimum. Oh yeah, this is another fun one. It's not just 1D time series. It can happen in images too. So this is an image of a brick wall, and then if you continually spatially downsample it, eventually when the resolution goes below the pattern in these bricks, you get these artifacts that get introduced into the images. So if you're taking pictures on, especially older cell phones, would do this quite a bit. I don't think anything on an iPhone, unless you're looking at something really fine. But so it can happen in images too, pretty much any data, audio, time series of stress, whatever. There's this thing that you should look up called the Nyquist-Shannon theory. Harry Nyquist, Claude Shannon, both big names in this kind of stuff, came up with this idea that you need to sample at a very minimum at twice the frequency that you're interested in. So if you've got a 10 hertz signal, you need to sample it at least 20 hertz. And that's the very bare minimum. In an ideal world, that gets you the peak and the trough of a 10 hertz sine wave. So you're going to reconstruct something that looks pretty bad, but you technically not lose the frequency content. Generally, as a rule, I would say you always want to sample northwards of 2 or 3 times that, more if you can, and you can always downsample later in your post-processing. But the bad thing about this is if you do alias data, so if you've got a higher frequency signal, even if you don't care about it, it will be aliased into your data, and you'll have no way to know it's there or to hear of it. A lot of the, one of the most common tactics we use is putting what's called anti-aliasing filter in front of our analog to digital converter. So we know that we're going to sample at, say we're going to sample at 100 hertz from our Arduino. Then we would put a filter in front of it that would have a corner frequency, say, so it'd be a low pass filter of maybe 30 or 40 hertz. So anything above that would be significantly attenuated and not make it into our data. Another big problem when you're doing data acquisition is signal integrity. Folks in our lab are familiar with this. If you've ever ended up trying to wrap some kind of pressure vessel or some kind of system in aluminum foil to try to get a clean signal, you're dealing with a signal integrity issue. It really happens. I've seen at very sophisticated facilities, people still having rolls of aluminum foil and trying to wrap connections to shield them. It's not something you want to do. You can eliminate this problem somewhat by using things like shielded wire. So this is, you can see the outer jacket of the wire. There are 4 conductors inside. And there's this copper foil apart anything that has high frequency components, anything that transmits radio signals, that kind of thing, in televisions, you'll see these metal boxes over the tops of certain components. And they're there for the same reason. They're to shield the components from outside electromagnetic radiation. Another gotcha, and this happens very often, I would say, in research labs, and folks don't realize what's happening and why it's happening. And it can really mess with your calibrations and make your data virtually invalid. A lot of times people look up the transducer, the sensor directly to the analog to digital converter, and that's it. And sometimes that's fine. If your analog to digital converter has what's called very high input impedance, which is something that we'll talk about later, you're probably fine. But more often than not, especially with things like here, we know the act of measuring your transducer or sensor can affect it. So you're flowing some amount of current into the analog to digital converter, it causes the voltage that the transducer is putting out to droop somewhat, and you get an inaccurate reading. And it's not necessarily always just a static offset. So it can really mess with you. To get around that, we put what's called a buffer in the middle. Buffer does exactly what it sounds like. It takes the transducer or sensor, it provides a high input impedance place for the transducer to go. And we even amplify the signal in here a lot of the time, though we don't have to. It'd just be a one-to-one buffer. And then it outputs something that the ADC can load down, and it's fine. It's going to make sure that it's always at the correct voltage. You're going to make buffers or buffer amplifiers a little bit later, once we actually have a chance to go over operational amplifiers and how to use them. Alright, so I'm going to show you some of the hardware that's available, places that you should go look if you need to do data acquisition. I would say that National Instruments is probably one of the leading data acquisition device providers, probably in all of academia, and they make fantastic equipment. This is the Pxi Chassis. So here we've actually got a full computer, like a Windows computer sitting here, and you've got all these cards that you can plug in to do different kinds of data acquisition. They have some that are specifically designed for temperature, some that are specifically designed for strain gauges, things that make you have to do less externally. And they also have these little small modules that just plug into the USB port of your computer. They're not as fast, they're generally not quite as accurate, but they're pretty good. You can look on eBay for a thing called MyDAQ, MYDAQ, that they came out with as an educational product a few years ago. You generally pick them up for around $150. You've got a 16-bit, several channel analog to digital converter, digital analog converter, all kinds of stuff in it. Plugs right into your computer. It's pretty handy to have in your desk and in your toolkit. They program their hardware with the LabVIEW programming language, which is this really nice graphical programming language. There's a LabVIEW training course coming up on campus in October. You can sign up for it. It's not already full. It's for folks who are new to LabVIEW, but it's a multi-day, really intensive course. And you need to have a laptop with LabVIEW on it. But this is what it looks like. So, for example, this box, there's a little arrow there. That would be a loop. You normally write for or while in a regular programming language. All these blocks represent different functions, then you wire them together. So it's a very different way to think about programming. And this is a relatively simple and pretty well laid out LabVIEW program. Unfortunately, when you start doing complex stuff, it looks like that sometimes. And if you need to do something that's very complex with LabVIEW, you either need to get advanced training or seek professional help in the sense of find somebody that is a professional LabVIEW programmer. Because something like this, there's no way that there's not mistakes in there that are haunting your data, and it's completely unmaintainable. But it is a pretty good tool. You just have to learn how to use it, and don't do that. So you've heard the phrase spaghetti code, right? From somebody's computer code is very disorganized. This is the visual of spaghetti code. Another company that's worth looking at is LabJack. These folks are out in Colorado, and they're in one of the suburbs of Denver. I can't remember which one right now. And they've made these different models. This is the U6, they've got the U3, they've got a bunch of different ones. These are really great little units, and they're pretty cheap. This was maybe $400, so it's less than or you can just use their program to grab data off of. It's a really handy thing, again, to have on your desk and have like. And then there are a bunch of other companies that make all kinds of stuff. I've had limited experience with several of them. DATAG makes products. Their software, as far as I know, is Windows only, and it's pretty old Windows only. I haven't seen them updated in quite a while. But they make some pretty good hardware. Omega makes a lot of the pressure transducers and things that we buy. They have some of their own data loggers. I've never used those. Onset Computing has what they call a Hobo data logger, which I think stands for something. I don't remember what. These are really nice because a lot of them have integrated, like you can pop an SD card into it, and say you want to measure water pressure in some pipe, you can just pop this in and pipe. It'll be waterproof and everything. This one's not. But they have a lot of really nice application-specific things. And then Measurement Computing is a pretty new company. I have not used any of their hardware, but I've heard some pretty good things, and they have up to 24-bit in a USB form factor like that. And there's also stuff that is very domain-specific. For example, for those in rock deformation, this is a deformation load frame. We've got a couple of pumps down here, and this is all manufactured by a company called GDS Instruments. They make their own data acquisition box that connects to their own hardware and their own software and all uses very proprietary protocols, so you're kind of locked into their system, but it all works together pretty nicely. And if that's what you need to do, might be the best solution. But good luck trying to program your own stuff as well. All right, so we're going to go back to the activity here in just a second. A few things I want to go over though. So your flex sensor is actually a bunch of conductive particles embedded in the little plastic membrane that's inside. You can see like the little black parts in there. And so when it's like this, its resistance, they say it's 30K. I measured mine, it wasn't quite that. It was something different. And then when you bend it, those particles are now spread further apart, so the resistance goes up. And it actually goes up in a surprisingly linear and nice way. Only bend it in this direction. Don't bend it in the other direction, it will snap. And that will be sad. Also be careful, this part down here where you plug it in is a little flimsy. It will kink, so gotta make sure you grab it. Excuse me. Alright, this is the voltage divider bit. So what you're doing is we're making this R1 a resistor that changes based on how much flex there is. And R2 is fixed at 47 kiloohms, so 47,000 ohms. You can calculate what the output voltage is going to be with this simple formula. So if the resistance here goes up, the output is going to come closer to ground. And if the resistance here goes down, then the output's going to get closer to plus 5 volts that you're driving it with. For the deliverable from this, email us a plot of data that you collect with me bending this. I will show you in a moment, because I have to take this back to the other side of the room since we're all flipped around today, and plug it in, how you can make